All right. Welcome, everyone. This is actually a great segue from Bruce's talk because we're to go into like the nitty-gritty details of how macros work and kind of learn how to write them from like a very basic level. So again, we're going to learn how to write less and do more with our code and also have fun. And again, I'm McCord, and a little bit about me is I work primarily in Ruby for the last 4 or 5 years professionally. Before that, I did a lot of PHP and Java. So Elixir has been my first foray into functional programming. But I got interested in it about a year ago. A prominent Rubyist, Jose Valim, had put this language out there. Books were being written about it. I use all of his open source libraries in the Ruby community, so I thought it might be worth a look. And while I was learning, I discovered the wonderful Erlang and OTP ecosystem, and it kind of blew my mind that this like nugget of innovation has existed, and I've been oblivious to it for my entire programming career. So since then, I've basically learned about process supervision, a whole lot of OTP, and I'm having the most fun I've ever had programming. And a large part of this is due to Elixir macros. So we'll hop in. What are we talking about today? So basically, we're going to go over what are macros. And Bruce touched on them a little bit, and we'll see how they work fundamentally as far as Elixir's AST is structured. Then we'll go into some of macro use cases as far as how can we eliminate boilerplate in our code to basically do things like remove dry code up, remove things that basically we otherwise would have had to write by hand or would have been very tedious to write by hand. How can we do like advanced compile type code generation? So how can we take like flat text files at compile time and do a bunch of code generation based off of the file contents? And how we can do neat things like compose domain-specific languages. So how can we almost operate at our own language level on top of Elixir to basically exist in whatever domain we're in? And lastly, how can we have fun with macros? Because that's why I'm here. Programming is a very creative process for me. So anything like macros that give me the power to explore the language and develop my own keywords are just a lot of fun, and I enjoy that a lot. And then we're going to go through like a guided lesson on writing macros. So we're going to implement an assert macro via slide, but it actually should go pretty straightforward because it turns out composing like little bits of code generation is the best way to write macros, and it works really well to show as a slide presentation. And we'll implement, in addition to an assert macro, we'll write our own kind of like mini testing DSL that's going to be like a bare bones version of EXUnit from Elixir's test framework. And we'll close with some real-world use cases and examples. So macros aren't these things to be avoided. They're not something that you should be afraid of. They're out there. They're being used in the real world. We'll go through and see how Elixir's unicode handling is using code generation at compile time to basically provide the best unicode support I've ever seen in the language. And we'll go through some examples of a web framework I started called Phoenix. I probably shouldn't call it a web framework because Bruce said that that's probably an incorrect term, but a application framework called Phoenix. We're using macros for the routing layer right now. We kind of have a really nice routing DSL, and we'll see how that works. So as soon as you get into macros, you'll find out that the first rule of macros is don't write macros. And you'll hear this from everyone who's into Elixir. This is on the website, on the macro section. And as we're getting into this, we need to keep thinking that macros are easy to get carried away with. So we can kind of get caught in our own web of code generation. They can make stack traces difficult to reason about, or they can hide basically the entire stack trace. And they can basically introduce complexity where a simple function would have been better in the first place. So having said that, macro rule number 1 is don't write them. Macro rule number 2, this is my rule, is use macros gratuitously. And this conflicts with rule number 1, but I truly believe to properly learn macros, you have to use a bunch of them and write them a bunch. So you'll hear don't write macros, and don't let that prevent you from learning how to write macros. Get in there, experiment, write a bunch of them to properly learn how to write macros, and then take a small fraction of that insight to apply to something you would use responsibly for a production system. So keep these two dualities in mind for the rest of the examples as we go forward. So what are macros? As we saw earlier, macros are essentially something that takes an Elixir code representation in and gives us an Elixir code representation back. So put more simply, it's just code that writes code. And as you get into this, you'll find out that Elixir itself is primarily implemented with macros. So a lot of keywords in the language, like unless, cond, def module, these themselves are macros in Elixir that is doing some code generation. So it's really neat that Elixir itself is leveraging macros at compile time. And you also find out that we have full access to Elixir, the language, at compile time. And to me, this is a really neat concept. So it's not this extra special half baked in feature of the language. It's full Elixir at compile time to generate our Elixir code. And when I mean full access to Elixir, I truly mean full access. Here we have a simple module called calculator, and then right in the module body, I have an arbitrary put statement that said any code can live here. And if we compile and run this module, we get that any code in here is valid statement out the standard out in addition to our function call. And this is because in Elixir, everything is an expression, and any code, any arbitrary code in a module body is totally valid. So it's not a large leap to go from, well, if we can embed like a put statement in a module body, what if we had some like dynamic function definition at compile time for our calculator? Maybe we could dynamically define some functions based off some operators and do a little bit of more advanced code generation. So keep this in mind that we can put arbitrary code in a module body, and it's totally valid in Elixir. And to really understand macros, we need to understand how Elixir represents code internally. And it turns out that Elixir can be represented entirely by Elixir's own data structures. And this is an extremely powerful mechanism because it allows us to have Elixir code represented in Elixir's own terms. So we can basically look into Elixir using Elixir's own terms, manipulate the code, and generate some other Elixir code basically in Elixir's own terms. And this is what allows us to write Elixir that generates Elixir, because it's all just our own native data structures. And you can get at this data structure by using the quote keyword in Elixir. So we can give it any expression. In this example, I'm giving it a mathematical expression, 1 + 2 - 5 × 10. And we can see we get back this very simple data structure. We get the operators as atoms, so like minus, plus, multiplication, and then the arguments passed to those operators we just get in a list. So it's this very simple data structure that we can then consume to either manipulate or do some other code generation off of. And we need to at least understand how this data structure works or be familiar with it to write macros, because this is the domain that they operate in. So quote, as we saw earlier, gives us back the representation of any expression, and that's the Elixir abstract syntax tree. And the AST is represented basically as a series of 3-element tuples. So all Elixir code that you write is always a series of 3-element tuples. The first element is an atom, usually representing a function call to perform or another 3-element tuple. Second element is metadata, and the third element is basically the arguments to pass to the first element, which is the function call, and that's it. So everything you compose in Elixir boils down to a 3-element tuple, and we'll use that in our examples going forward. And here's a couple examples. So if I have a div, which is a built-in function in Elixir to divide two numbers, if I quote that to get at the representation of the div invocation, I get back a 3-element tuple. The first element is the atom div, because that's our function call name. We don't have any metadata. And then the third element is just a list of arguments that we pass to div, 10 and 2. So it's this very simple, straightforward transformation from the Elixir code that you write to the AST representation. And then we can kind of see how this stacks on top of itself. We take an add function, we'll define an anonymous function named add. It just adds two numbers, returns the result. And if we quote the invocation of add, we see that we get this like stacking 3-element tuple. So if we quote that, we get a 3-element tuple whose first element is another 3-element tuple. And if you read through this, it reads very similar to our Elixir code. We can say that colon dot, that's just the atom dot, it's a dot operator. So we can almost read through it as apply the dot operator to the function add, pass in the arguments 1 and 2. So for me, it's this really neat, that it's just a very simple mental exercise to go from the Elixir representation to the AST representation. And we'll use this going forward to write our assert macro. And for anyone in here, even after this talk, I recommend going home and writing an assert macro as your first macro in Elixir, because it really shows off how you can consume the AST and how you get the representation of code versus the evaluation. Because if we go into a lot of languages, I'll pick on Ruby, for example, we have, like for our testing frameworks, we have an assert function or assert method that takes a Boolean result, and we have things like assert equal. Same with like JavaScript testing frameworks, many languages will have these assert and assert equal functions, because if you wanted to assert that or test that two numbers were equal, you could say assert number 1 equals number 2. If that test failed, all you would get was test failure, we got false, we expected true. So we lose the information in our test, so we had to devise some other functions in these other languages, like assert equal, to maintain that information. But in Elixir, since we have the representation of code in a macro, we can write a single assert macro and basically shove any expression to it, and it will be able to maintain the data of that test and give us a very helpful failure message. So before I begin writing a macro, the first thing I do is fire up IEX, which is interactive Elixir, and I basically feed it some expressions that my macro is going to take in. So if we write an assert macro to assert like 2 numbers are equal, I'll basically quote that and say, okay, what does like 5 equals 5 look like as the AST is concerned? And as expected, we get a 3-element tuple whose first element is an atom that represents the operator. It's going to be : equals equals. Because it turns out the equals equals operator in Elixir is just going to be referenced off the kernel. We have some metadata here that we're not going to really be concerned about. And then we have the arguments of the left-hand side value and the right-hand side value that were passed for equals equals. And the same thing for greater than. If I want to assert that 2 numbers are greater, or one number is greater than another, if I quote that expression, I can see the operator is just the atom greater than, and then my left-hand side value, my right-hand side value. So basically, starting macros, hop into IEX, use quote, see what the direct AST looks like, and then use that to drive the design decisions of your macro. And here's our first Elixir macro. So macros always have to be defined on modules. So we'll create a module named assertions, and then we'll define a macro with def macro. And we'll name it assert. And a core concept here to realize is our macros get the literal AST from your code. So we can pattern match on that directly. So if you notice, since we can quote like 5 equals 5, we've got a 3-element tuple. Well, our assert macro can just pattern match directly on a 3-element tuple because all Elixir code is represented as a 3-element tuple. We know that the first argument is going to be the operator, and then the last argument is going to be a left-hand side value and a right-hand side value. So we'll pattern match on that directly. So we can say our first element is going to be some operator, bind that to a variable. Second argument is metadata, which we don't care about in this case. We'll discard it. And the third element we know is a 2-element list. We'll pattern match and bind directly on the left-hand side value and the right-hand side value. So we're pattern matching directly on the AST, and then a macro's job is to take in an AST and return an AST, so we use quote. And quote's going to start some AST generation, and all we do is basically a tiny bit of code generation. We proxy this to a doAssert function, and then we use this odd-looking unquote thing that Bruce introduced a little while ago. And the best way to think about unquote is, and quote and unquote together are almost like string interpolation for code. So if we have quote, we're starting some AST. If we want to interpolate some values into that AST that we're generating, we use unquote. So it's almost like if you had a string, you're starting a string, you want to insert a variable value into it, unquote would do that for you. And we have to do this because if we didn't use unquote here, we just said operator, left-hand side, right-hand side, those would actually, at the call point, be local variables that didn't exist. So we want to inject these values directly into the AST here. And then all we do is we have to implement our doAssert functions. And these are very straightforward. Since we have the operator that we passed in, we just pattern match on it directly, and we can say, well, if you have the equals equals operator, when the left-hand side value is equal to the right-hand side value, print a period because we know we passed. Any other clause, we know we failed, and we can print a very helpful failure message saying that we got a failure, we expected the left-hand side to be equal to the right-hand side. So we've retained that information that we passed to the assert macro because we have the representation of code. And then we would basically continue to do this for every operator in the language. We can say, okay, do assert when you have a greater than operator. When the left-hand side is greater than the right-hand side, print a period. Any other clause that we've matched, we know we failed. So we can say we expect the left-hand side to be greater than the right-hand side. So again, we retain that information. And we basically would continue to do this for every operator in the language. But they would all look very similar to these function bodies. So I'm not going to continue that here. So then to basically consume this macro, we'll create a module maybe named myTest, import the assertions module to pull in the macros and other functions it contains, and then maybe like write a run function and make some assertions. And if you notice, we have a couple failing assertions, like asserting 5 equals 0, asserting 0 is greater than 8. And if we run this with myTest.run, we get a couple of passing tests, and then we get those test failures with very helpful failure messages. Because again, we got the representation of 0 greater than 8, not the evaluation. And you might be thinking, oh, this is pretty nice. And it does our assertions for us, but wouldn't it be nice to operate at kind of a higher level? We had to like write our own run function, and then we didn't get any kind of like test case description. Wouldn't it be nice if we could give it some kind of string test case description, and in addition to the failure messages that maintained our information, we had some kind of test case description to give us an idea of what we were trying to test. So we'll implement this as a test macro and like a test DSL similar to EXUnit, just to show you how easy this is to compose. And this is where use comes in that we saw earlier. So use is just a macro that provides a common API for extension. Since any kind of module can have a macro on it that does any kind of code generation, use is just a very simple mechanism to say, I want to do some code generation on this module, and that's it. So we can use this use mechanism to produce something like this. So our goal, basically for the next 4 slides, is to implement what you see here. We want to be able to say def module myTest and then say use assertions. And then within that, we can then just use a test macro and a string description to say test adding 2 numbers, give it a block of code between a do and end, and then make some assertions. And this is cut off a little bit down here. And then wouldn't it be nice if we just defined a function named run automatically for the user so they didn't have to define their own function to run all their tests? And that's what we'll do here. And you can see we have a comment up here that says the use assertions, all that does, all use's job is to invoke an __ using hook or using macro on the module passed in. And we'll see how this works in a moment. So again, our goal is if we run that test, we get a failure, but we also get the test case description that we were trying to test 0 is greater than 1. And obviously, we expected 0 to be greater than 1, so this test failed. So how will we go about implementing this? Well, we need a test macro. But before we get started, we have to open up our assertions module that we just created, and we have to implement that using macro. And this is just this is all using is literally this simple API for common extension. And our using macro just does a few things. It's going to import the current module we're in, which is the assertions module. And this is just a convenience so the user doesn't have to write import assertions like in our first example. And then it does something very important. It defines a module attribute on the module being defined named tests with the accumulate true option. This is cut off here. And what accumulate true does in this case, it says anytime at compile time that we assign to this test module attribute, we want to accumulate that in a list of assignments or a history of changes. That way, during compile time, each time we say test, we can shove a value into it and keep that growing in a list of assignments. And then the last thing we do is set a before compile attribute, which is another hook in Elixir that says, just before this module is done being compiled, that very last end block you get to, invoke this before compile hook to do a final bit of code generation from our assertions module. And obviously, we need a test macro, so we'll implement it. And we'll say def macro test. And our test is just going to take a string description, and then we can pattern match directly on the do end contents. Because if you're familiar with Elixir, everything between do and end is just syntactic sugar for a keyword list who has a single key of do and whose value is some block of code. So in our test macro, we can say, well, take some string description, and then your second argument, pattern match on the key do, and the test block is going to be some AST of code, which is everything between the do and end. Then we convert the function name to something that can be invoked as a function on our module. So if you said test 0 is greater than 1, we would convert that to a function name of 0 _ is _ greater _ than 1. And then we just do a little bit of code generation. So this bottom quote here will say, OK, do a little bit of code generation here, assign to that accumulated test module attribute, and basically give it a tuple of the test case description as a string and something that we can invoke to call this test. And then we define a function that was the 0 _ is _ greater than 1, whose function body is literally everything between the do and end of our test macro. So is everyone clear on this? Because it's a little bit hard to get into this initially, but everything between the quote do and end at the last bit is code generation that we're performing on the module that said use assertions. And all we're doing is 2 lines of code generation to say, hey, remember this test case description, save a test function that we can invoke to call this test case, and then literally define the function whose body is everything that we gave between the do and end of our test macro. Yeah, go ahead.
Okay, so that line there, like throw me for a loop just because I don't know how to parse Elixir yet.
Which one here?
It looks like you're defining a function called unquote, but you're actually defining...
Right here?
Yeah, you're defining a function of the name of func name unquoted.
Correct.
Okay, so unquote is a keyword. It's not gonna, you can't define a function called unquote.
If I tried to write,
That's a compile time construct, right?
Ah, okay.
So you're saying def, that's basically
Yeah,
There
so
we go.
we're doing some we start some code generation here with quote. We've defined a function name, which is just going to be an atom, and then we give that to def, which it turns out def is just a macro, right?
Your color coding,
Yeah.
Bruce, last slide.
And the tests we were accumulating, you're just passing that into the tests?
So this module attribute here,
Yeah.
you'll see how that works in a moment. So at compile time, every time, like at the top, every time we say test 0 is greater than 1, it's going to store basically remember that description as well as what a function it can invoke to call that test case. And each time, if you had another test, if you had like 4 of those, it would accumulate that in a list. And then we'll use that in a moment at using our before compile hook to actually do something special with it. So at this point, as the first compile pass is coming through, it's just remembering the test case description you gave as well as defining a function that you can invoke to call the test case. But yeah,
Why do you have to do the import
up here.
in the using? Yeah.
So import, all using is literally this def macro using. All it is it just invokes the assertions underscore underscore using underscore underscore macro. So if we go back to our ideal world example, what we want to use here, all use assertions here does is literally calls assertions underscore underscore using underscore underscore, and that's it. And that does some code generation and returns the AST back.
But then import underscore underscore module is importing my test.
No, import underscore underscore module here is saying we're within the assertions module. So underscore underscore module, since we're unquoting, I could have replaced that with assertions to be clear. But if we rename the module, this would pick up whatever module we're in. So this line is literally just saying import assertions. That way the user didn't have to themselves.
But use doesn't do that. Use just invokes using.
Yes, correct.
Okay.
As the common API for extension. That's its sole job. And it's up to the person implementing this to do import
So
their
you would
module.
almost always do import.
Yes, almost always. And you can do multiple imports. So our last bit of this is we've accumulated these test attributes. Is everyone clear on this? Any more questions on this? We have to write our before compile macro. And this is where I think your question came in, that we have one job, and our job is to implement a single function named run. So we start a quote, and we write a function named run who can then reference that at tests, and that test module attribute is going to be a list of every assignment during compile time containing a list of tuples of our test case description and a function that we can invoke to call that function that we generated to run our tests. So then all we do is just iterate through each of those tuples, invoke the test case using apply on the module because it's just an atom, pass it to a report function, and our report function received a slightly modified version of our assert macro that we wrote earlier that instead of printing just returns OK or failure in a failure message. So all we have to do is print our failure message or our failure description as well as the message that our assert macro was doing in the very first assert example. And that's it. So this is all that was required to implement a very simple test DSL in Elixir. And this is how we would use it. And I have a couple comments to show you as like the first compile time pass, like what's happening. And we'll like go through this top to bottom. So I can say def module my test, and then I say use assertions. That invokes the underscore underscore using macro. And that imports all of the assertion functions as well as the assertion macros. And then it creates an accumulated test module attribute. And then it says, hey, just before you're done compiling this Elixir, invoke a before compile hook on our assertions module. And that's all it does. And then it starts stepping through this. It hits the first test macro. And it says, OK, see the comments above that. It says, remember that the test case description was adding 2 numbers. And then convert that to something we can define as a function named adding 2 numbers. And then we'll define that function that we can then invoke later. And then once Elixir gets to the very bottom end here, it's going to say, OK, I'm done. Is there a before compile set? There is, so invoke that before compile hook on the assertions module and do a final bit of code generation that just defines a run function, which iterates through all of our tests and runs them, reports failures. And then we can just say mytest.run, and we get very helpful failure message saying, well, you were testing 0 is greater than 1, and like, duh, this failed. We expected 0 to be greater than 1. Obviously, this is a failing test. So if we can grasp this, you've grasped, I guess, how macros work at a fundamental level. So if anyone's unclear here, feel free to ask questions at this point, because this is supposed to be like a guided lesson. So before we move on to like some more complex examples, I'd love to clear some confusion up at this point. So everyone clear on this? Okay. So we wrote our first assert macro. We wrote a testing DSL. That was pretty neat. And that was very similar to what Elixir is doing in its EXUnit test framework, but a very basic version for learning purposes. But that's essentially, if you're writing EXUnit in Elixir, you can pass anything to assert, and you get those very helpful failure messages. This is because it's just using macros and getting the representation. But we can also see some like real-world use cases. If we check out Elixir's Unicode support, we'll find out it has like fantastic Unicode support. And if you're getting into like how it's doing it, you might say like, oh, well, that's not very cool. Like, string support, what's the big deal? But if we check out like a lot of mainstream languages, like I'll pick on Ruby, for example. If I want to take like the string thanks Jose, for this awesome language, but I want to uppercase it because like I'm super excited about Elixir, it doesn't quite work in Ruby. You can see like the E in Jose is not uppercased. It didn't properly map that code point. And this is like the latest Ruby version that just shipped. And if you're like a Rubyist, you would think that Ruby has like really excellent string support and string manipulation, and it does, but it cannot properly map these Unicode code points. But if we check out Elixir, uppercase thanks Jose, and like bam, we get the proper uppercase version of E, and then it doesn't garble the code points in the E and L in the reverse example. So this shouldn't be that surprising, but go try this in a lot of mainstream languages that you're using today, and they'll likely fail this test. And once you want to investigate, like, how is Elixir doing this, you'll find out that it's extremely simple, and it like put a huge smile on my face looking through the source code. And hopefully I can convey that here. So how is Elixir doing this great Unicode support? Well, it turns out that Unicode is handled by pattern match function definitions that are all generated at compile time. And they're generated from a text file named unicode data.txt, and it's basically a giant code point database that's checked into the source code repository. And at compile time, it goes through, opens this file up, and then at compile time defines like thousands of function definitions doing that code point mapping. And then it lets the virtual machine pattern match on each character to do the proper code point representation to like convert a string to uppercase. And the cool thing about this is like to support any additional code point in the future, all we do is open up a text file, save it, recompile Elixir, and like bam, we have support for it. So it's a really neat mechanism and a really great example of what you can do with code generation, and probably my favorite example to date. And we'll see how this works in the next couple slides. So if we open up that unicode data.txt, we basically get like a semicolon delimited list of code point mappings. And if you notice, and this is like 20,000 lines long, this unicode data.txt file. If you notice at the bottom, there's like a rocket, helicopter, high-speed train. Those are all like emojis. So Elixir has great emoji string handling support because they're all just Unicode code points. We add them to a unicode data.txt file, and like we're done. So to me, that's a lot of fun. And here's an example. If you open up the Unicode EX file in Elixir Standard Library, this is not the entire file, so don't be tricked. But it is surprisingly succinct, and I pulled out the interesting bits from our previous example with Ruby versus Elixir. And we'll kind of walk through this. So I think this is basically all the bits to generate uppercase string handling support of Unicode code points. And we'll walk through it. So on like line 2, we open up a Unicode data.txt file, read that into some data path. And then on line 3, we'll basically, I've cut the line off, but all it does is it parses that Unicode data.txt file by semicolon and reads that in to that codes variable, and that's going to contain a bunch of Unicode code point mappings of that entire file. Then it defines a single public upcase function that takes a string, and it proxies to a doUpcase function, passes in that string in. And like the last 5 lines are like where the magic happens, so I'll probably like repeat myself how this works a couple times. But like LC is a list comprehension, and it's basically saying go through every code point mapping that you read in from that Unicode data.txt file, define a private function named doUpcase, pattern matching on the code point, and then returning the uppercase mapping of that code point concatenated with the recursive upcase of the rest of the string. So I'll repeat it one more time. We go through every Unicode code point mapping that we read in from Unicode data.txt, like 20,000 lines. And we say, if you have an uppercase version, define like hundreds or thousands of functions all named doUpcase, pattern matching on the given code point, returning the uppercase mapping, and then recursively upcasing the rest of the characters in the string. And just to drive this home, like how simple this is, like these top 2 examples are literally defined in everyone's compiled Elixir Unicode module. After you compile this, there will literally be a function defined at the top, matching on like the E, and then returning the proper code point mapping to the uppercase version. And the neat thing that the code generation gives us is we can basically define very succinct composition of the Unicode module, and we also get high performance. So we're leveraging the virtual machines like pattern matching engine to say pattern match directly on that binary character and then return the uppercase version. So like, the BeamVM has been optimized for decades, so we can leverage the pattern matching engine to literally have like hundreds or thousands of do uppercase functions. Just pattern match on it, we don't care, whatever it is, pattern match, return us the uppercase version, and then continue recursively on the rest of the characters. And if you notice, like a rocket emoji, like literally if you tried to uppercase a rocket emoji, it would just say like, well, I had no Unicode mapping for it. Just return the rocket emoji and then uppercase the rest of the string. And so for me, like this is the best example I've seen of code generation at compile time, and hopefully this gives you some example of like the kind of power that Elixir gives you and the kind of neat things you can do productively at compile time. Because this would have been impossible to do by hand, or I guess you could have literally defined do upcase for every code point mapping in the language, but that would have been very tedious and it would have been much harder to maintain. And then we can do other neat things. So I started a web application framework called Phoenix that we're using macros for like the routing layer. So we've created a routing DSL that might look familiar to you if you're coming from Ruby. And we can just say like def module router. I can then say use phoenix.router, which we saw before is just going to allow us to define some macros, import some functions. And I get this very nice expressive DSL layer where I can say like get to some kind of pattern URL, map that to a pages controller, and then call the show function. Or I can say like resources users, map that to a users controller, and that's going to generate me some like RESTful routing automatically. And you might be thinking like this is really pretty, but like is the code generation crazy? Like is this hiding complexity or maxing complexity underneath where we wouldn't necessarily want to introduce into whatever app we're building? But it turns out this is actually pretty straightforward. So if I say get to pages and then colon page is kind of like an idiom for we want to say if it was like pages contact, pages about, we want to have a name parameter whose name is page. The code generation for this is like 3 lines of code. So when the macro for get pages colon page, all it does is generate the code that you see here. It generates a function named match, pattern matching on the request type, which is get, and then it splits the request path by /, and then pattern matches on each segment. So we have like pages as a string, we'll pattern match on that directly. But then we can generate an AST at compile time that says instead of matching on like that colon page as a string, generate an AST that is going to literally create a variable named page and then bind whatever was in that second element to the value of page. And then we merge that onto any of the middleware query string parameters with the name page, and then we invoke our controller function show. So literally, there's no extra complexity going on here. At compile time, that top get macro is just producing these lines of code that you see here. And again, for like a get to files and then asterisk path, it's very similar, but there's a slight difference in the code generation. We can take asterisk path to mean that's like a splat name parameter. We want to be able to match like /files, /documents, /images, /whatever.png. We want to have path be a named parameter that matches anything after that second /. And it turns out we can do this with head-tail pattern matching in Elixir. We just generate a function match again, pattern match on the get request, and then we do a head-tail pattern match that we're able to generate at compile time that's going to pattern match on the string files. And then since we split the URL by /, that path variable is going to be another list containing the entirety of the rest of that request path split by /. So no matter how many segments there was, it would match on everything. And then we add that to the query string parameters for the middleware. We rejoin the path to make it something more digestible for the user. And then we invoke our controller function show on the files controller. And that's it. So it turns out that when you compile this router that you saw in a couple slides ago, so everything you see here, after this is compiled, your router module will look something like this. I've removed the function bodies just so I can fit this on a slide. But it literally, every macro, get, post, put, delete, are just going to define a function named match, and then we're going to let the virtual machine do all the work. And the neat thing about this is it's highly performant. So literally, almost 100% of request or router dispatching is handled by the Erlang virtual machine. So a request comes in from the web server. We have the request path. All we do, the only work that we do is we split it by /. Then we literally say, we call the function router.match, pass in the request type, and then pass in that list. And the virtual machine does like 100% of the work to actually match what controller function to invoke. And Jose did this first, so the first time I saw it in the Dynamo framework. So this idea was not my own. But it's a very neat way to handle route dispatching because most languages that have like a routing layer, they'll build up some kind of like map in memory. So they'll basically go through every time you define a route at runtime, they'll say we got a request. Does it match this regex? So the first route, no. Does it match this one? No. And it will just kind of go through. And it's much slower than the approach here where we're literally just invoking a function, router.match, let the virtual machine pattern match on it. It's highly performant, and the code generation is straightforward. And just to kind of illustrate how this happens is we have a couple DSL layer where I say like resources users, and then I can nest resources comments, so we can nest macros. And if a request comes in as like a GET request to the server to like myapp.com/user/1/comments/2, all we do is split that request path by /, and then you can see how the pattern matching takes over here. We literally just invoke the function match, which is all that exists, and it's going to pattern match on the first segment users. But then if you notice, we were able to generate an AST instead of saying, hey, we want to match on the string. We were able to generate the AST at compile time that says, no, we want a variable named user ID. And we want the value passed in to be bound to 1. Same with comments, pattern match on the third segment, and then at the end, pattern match on the comment ID, but bind that to a variable named ID. So we get the pattern matching for free, and then we get the binding to our query parameters for free, basically by the virtual machine. Same thing for like files/asterisk path. It's a very similar operation, but it's doing a head-tail pattern match on the list that you see at the bottom. And this is, again, is 100% by the Erlang virtual machine right here. It's just taking this list and it's able to say, okay, first thing is files, do a head-tail pattern match that we're able to generate at compile time, and then path is going to be the list docs, photo, image.png. So you might be thinking like, this is pretty, but it's fancy, it's neat. The code generation isn't that crazy, but the first row of macros was don't write macros. All we're doing is a single function definition. Like, is this enough of a win? You might be asking yourself. Like, all it is just this pretty layer, but we could write these match functions ourselves. And that'd be totally valid. So you could open up in Phoenix and say def match, pattern match on some list, and that'd be totally valid and it would work. But we can do some extra work for the user. So there are some more wins that we can gain other than a single match definition. We can generate named route helpers. So anytime you say like get to pages and then :page, at the end there I can say as page. And I can say, hey, name this as something I can call later to rebuild this path. And then at the bottom, I get, after my module is compiled, in addition to the match definition that's invoked, I also get a router.pagePath function defined for me. Then I can pass in a keyword list. I can say, hey, router, give me the page path where the page is home, and that regenerates that request path of pages/home. And then with like the fancy resources route generation, gives me some other like nested conveniences. So if I said resources users, I want to nest some other RESTful comments resource, I get like a router.user comment path. I can pass in the query string of each name parameter, or I can pass in a keyword list of each name parameter, and I get the request path reconstructed for me. So macros are used here for a couple conveniences, and then we can extend this in the future to do some other things. So for me, this is a big enough win over writing just simple function definitions. So lastly, I said that macros can be used to have fun, and hopefully all this was fun. So like writing macros day to day for me is a fun experience, but we can also do like crazy things that you would never want to ship to production. But they're fun, and that's what programming is all about for me. So I came up with an example here. I wanted to write a module that I could say, hey, launch a web browser to any GitHub repository that I have in my profile. And I can just define that as a function. So I can say like github.go Phoenix, and it just launches a web browser to the Phoenix Framework project webpage. So we can do that in a single slide. It's like 15 lines of code. I can say, okay, def module hub for GitHub, and at compile time, take the string to my github.com/chrismccord.json URL, transform that into a GET request, make that GET request, pull out the request body, decode it as JSON, go through each JSON result and define a function whose name is whatever the GitHub repository name is, and whose function body is literally the keyword list parsed from that JSON request of like my repository information. And then I define a function named Go. It takes a repo name. It calls my max OS X open command, and it calls the function of whatever repo it was, and then it pulls out the URL, launches the web browser there. If we wanted to see what that looks like at runtime, literally I could just say like hub.go Phoenix, and like bam, it launches my web browser to github.com/Phoenix framework. I can say like how many watchers are there on the repo? Hub.Phoenix watchers is going to call the Phoenix function, pull out the watchers, and I can see last time I compiled this, I had 103 watchers. Hopefully I need to drive home that everyone needs to realize that this is the GitHub API request happened at compile time a single time. At runtime, this JSON information was embedded directly as function definitions. And I guess it's pretty crazy. Like I don't know that you would ever want to ship code that like relies to even like build on a third-party API being available. But this is pretty fun. Like for me, like this is like the fact that this fit on 15 lines, and this is just straight Elixir writing, like generating Elixir code, for me is like something that I've never seen in a language, and it's really fun, and hopefully shows what you could do. I don't know that you'd ever want to do this, but maybe this could inspire you to do something in the real world.
Never want to do. Could you have a text file that had some stuff in it and then some Elixir code, and then like eval that into the AST?
Yes.
File time?
Yes. There's a Elixir. You can basically say like eval the string and give me like the quoted AST back, and you could totally do that.
Awesome.
Like I don't know why you would ever want to, but do it. So like,
Are you missing a line up here?
what's that?
Are you missing a line up here?
Where at?
Like a def macro line?
Anywhere in here?
Yeah, like line 2 doesn't seem to make sense.
This line right here?
So like you have def module do, and then
Yeah.
like is there, remember,
So like
Any arbitrary code is valid.
in a module. So like I have a def module hub do, and then I can literally put any arbitrary Elixir code here.
all right.
So I start with a string.
I'm seeing one too many ends up there.
Oh, there's it cut off. There's an end down here, but
Maybe saying you saw one too many.
I'm still seeing one too many.
The function, the anonymous function, I think is the other.
yeah. So enum each has an end here, and then we're good on our ends. Okay, so I'll close with like as far as like doing crazy things. Like if we review our macro rules, and like this is the very important concept to drive home. Like what did we learn today? So we learned that like one, we shouldn't write macros, and you'll hear this time and time again from everyone. And I want everyone in the Elixir community to stop saying this and to say we should write macros responsibly. And I say this because we don't want to prevent people from exploring the language. And also this would ruin my second point of we should write macros irresponsibly. And I truly mean that. So like there's a duality here, but like I'm of the opinion that to properly learn macros, we have to get in there, get our hands dirty, and write a bunch of them. We need to be irresponsible. We don't need to be like concerned that we're doing something crazy. We want people to get in, like get their hands dirty, and properly learn these things. And like 90% of like these crazy things you write probably isn't something you want to ship to production, but it could give you insights on ways you could write macros in a responsible way to a library that you would ship to production. So keep this in mind, and I would like actually the documentation to be changed to say, get rid of the first rule, even though it's kind of funny, and say like, just be responsible with these things. We can get carried away. Use a simple function if a simple function would suffice, but if we can do something extra, let's do it, but let's do it in a responsible way. Let's make sure it's well tested and make sure it's well documented. Then two, explore. Write your responsible code and have fun. Because you'll undoubtedly, like if you do something crazy, like evaluating strings in a text file, you're not going to ship that as a third party, at least I hope you won't. But you'll undoubtedly like understand how the AST is structured fundamentally, because you'll have to like explore and learn how these things work, and then you can take that exploration to apply to something that you would do for a production system. So it's like a win-win. It's fun, and you can also use it as a learning experience. So that's all I have. I'm Chris McCord on Twitter. You can reach me by email. And I pretty much idle and live in Elixir Lang Freenode IRC at all times. I worry about being like too active on there, but I'm always willing to help. So if you have any questions or stumbling blocks, hop on there. There's a lot of helpful folks. Jose's in there all the time, and he'll help you out. And github.com/Phoenix framework is where you can get access to Phoenix. We're looking for collaborators, ideas. It's very early, but we have some ambitious goals, and I'd like anyone to hop on and contribute. So if there are any questions, I'd be happy to answer them. Yep.
So if I read it right, the pipe that you used in your assertion framework to get from the string to the function name in
technically, yes.
Yeah, right. So you could just make that a bijection, but that wouldn't be any fun. Like, what's the
Yeah.
most macro positive, idiomatic way of handling something like that? Right, because now you're having to have parts of the generated code inspect.
Yeah, so you're saying like this function name, theoretically, we're just stripping out alphanumeric characters. We could end up with clashing functions.
Right, and so it'll fail in a funny
Yeah,
way.
the nice thing, so like I actually realized this after I wrote it, but I left it because it wouldn't have fit on this slide here. But the nice thing is that the VM will warn you about that. We wouldn't want to ship the library like this. We could do other things. We could make it not friendly. We could append, like, since we have the test module attribute, we'd actually check it during compile time and maybe append a number of like the test case. How, like, is this the third one? And that would potentially make it unique. We could do some other things. Yeah.
Yeah, but the function name can be any atom, so you could just call binary to atom and leave it with spaces, whatever you want in there.
Oh my gosh, you're totally right. Yeah.
And it's, yeah, I mean,
So we could
Just a single quote.
we could literally convert this to just an atom with and that'd be totally valid with the spaces. So Jose, you'd only be able to invoke that via like the apply function, right? You wouldn't be able to.
if it's an atom, you can.
But I wouldn't be able at runtime. Would I be able to call that function define?
So you just need to, you can say like.
Apply.
Test dot open quotes function name whatever you want to put in there, close quotes,
And that would invoke it.
and that would call like any.
Gotcha. Awesome. Anybody else? Yep.
Are there, I mean, is there like a list of stuff that you might find in other languages, like inheritance, polymorphisms, that metaprogramming is the solution for? Is like, I mean, you define the language of macros, like, are all those other sort of goodness, like, is that how you find it in Elixir?
As far as like replacing like inheritance or.
Yeah.
For me, so I like to think of macros as just a few use cases. Like you could do like absolutely crazy things. You could probably like implement your own inheritance layer. But like for me, it's about making things more convenient, or doing things at compile time, like going through a flat text file and generating some function definitions. But really, the sky's the limit. So it's almost like we can define our own layer on top of Elixir, define our own keywords in language, essentially. So you could do almost whatever you want to do. But at least for me, it's really defining like a couple things. Like DSLs are big for me, defining my own layer in the language. And then secondly, it's like generating hundreds of functions that I would have otherwise had to write by hand. And that's kind of where my thing stops. But yeah.
There's a great article called Hackers and Painters. It's by Graham, really old one, probably a lot of people here have read. And he basically has a great point about the power of various languages. And he always put Lisp at the top of the list because it's macros. I mean, basically any place, anytime, any place that the language comes short, you can normally patch with macros. Templating is just, it's a game changer. It's the game changer for a language.
Yep. And speaking of Lisp, like the first time I saw this 3-element tuple, I don't come from a Lisp background, but I was like, this is basically like Lisp, but like we replace brackets with parens, like very similar idea, and that was really cool to me.
So the idea that in Lisp, this would actually be executable code, but what Jose has done is separate the primitive syntax from the syntax tree. So you have a simple, uniform syntax tree in the macros, and that's something that no other language has done. I think it's powerful.
And Chris said like that module that they are all implemented in Elixir itself. And the point is that the same constructs you're using to build the language, it's available for you to extend the language, right?
That's it. That's all I have. Oh, go ahead.
So if you were to try to push beyond the bounds of the language definition, so for example, implement destructive assignment or lazy evaluation, are there people who have you or has anybody of you tried to do that with?
So there, you can define a macro that defines its own, like by default variables you define in your macro are like hygienic. You could also pass a option that says any variable I define here, I want to be able to clobber some outer scope variables, and that's doable right now.
So for example,
So you could do,
implement a loop construct.
yes. I see no reason why you wouldn't be able to, but you are ultimately bound by the constructs of the language. But as long as it can take in some kind of valid AST, I could implement like a loop macro, give it some valid Elixir code, and it would be able to take that in, manipulate it, do whatever it wanted, and spit an AST back out. But that's all I have.